Shalom and thank you for joining the Technion Physics Department's podcast, the Technion FIZZICAST. My name is Efrat Sabach. I am a Technion Physics graduate, and I'm pleased to interview Professor Jeff Steinhauer. Jeff is a faculty member in our department. He studied physics at Stanford University and joined our department in 2003. Jeff studies important analogies between ultra-cold atoms and other areas of physics. For more than a decade, he's been focusing on Hawking radiation from sonic black holes. Shalom, Jeff, and thank you for joining me.
Thanks for inviting me, Efrat.
First of all, can you give us a brief explanation of what is Hawking radiation?
Certainly. In 1974, Stephen Hawking predicted that a black hole should radiate light and other particles. This is surprising since naively a black hole does not radiate anything, hence the name black hole.
I've heard that Stephen Hawking's prediction that a black hole should radiate was revolutionary. What was his source of inspiration, or did his ideas simply appear out of thin air?
Actually, Jacob Bekenstein was an important source of inspiration for Stephen Hawking. Before Bekenstein, it was believed that black holes had no history. In other words, it was believed that black holes were like atoms. Each atom of a given type is the same as the next. It doesn't matter what occurred to an atom in the past. Its history left no mark on it. Similarly, it was thought that all black holes of a given type were identical. The type of black hole is specified by its mass, its rotation speed, and its electric charge. It was believed that if you would know these three properties, you would know everything about the black hole. Jacob Bekenstein changed all that.
According to Bekenstein, what were the other properties of black holes other than mass, rotation speed, and charge?
Bekenstein asserted that black holes contain a complex pattern which can be completely random or it can contain information. Information is the opposite of randomness. For example, an intricate pattern in the form of letters can tell a story, but random markings on a page do not. Random or not, the pattern means that not all black holes of a given type are the same. Bekenstein did not stop there. He also said that the entire intricate pattern exists on the surface of the black hole, rather than in its interior. This led other physicists to invent the holographic principle, which states that everything about an object is specified on its surface. You can judge a book by its cover. More than that, if you had perfect knowledge of the cover, you could know what is written in the book.
What determines how random a black hole is?
Typically, warmer objects have more randomness than colder objects. Stars have lots of randomness. In that sense, Bekenstein said that black holes are like regular stars. They also have randomness. The temperature of a star or a black hole determines how much randomness it has. Bekenstein and his theories annoyed young Stephen Hawking to no end. That is, until Hawking accidentally proved Bekenstein correct. He proved that a black hole not only has randomness like a star, but it also radiates like a star. It radiates Hawking radiation. The color of radiation is determined by the temperature. For example, a relatively cool object like a person's body radiates in the infrared, whereas a warmer object like the sun radiates visible light. Bekenstein and Hawking both found the same temperature, which determines both the randomness and the color of the Hawking radiation.
So Hawking radiation from a black hole is light, like the light from the sun?
That depends on the temperature. The emission of higher energy particles requires higher temperature. Stephen Hawking predicted that in general, a black hole could radiate a broad spectrum of particles, including all particles with positive energy. That includes basically everything: particles of light called photons, electrons, gravitational waves, etc. A typical black hole should radiate like an ordinary star, but a star with an extremely low temperature. Our sun has a temperature of 6,000 Kelvin, but a typical black hole might have a temperature which is 100 billion times colder than that. That means that the outgoing Hawking radiation is radio waves, but there is also radiation falling into the black hole, and that radiation is extraordinary.
So the black hole radiates like a cold star. But why is there also radiation falling into the black hole? And why is it special?
For each particle of radiation exiting the black hole, there is a particle which falls into the black hole. This particle has negative energy. That is a strange statement. What is negative energy? The reason that negative energy particles sound so alien is that they do not exist in our world. They only exist inside a black hole. That is why only black holes radiate Hawking radiation.
If negative energy particles do not exist in our world, how can we understand them?
We don't have negative energy particles, but we do have negative energy quasi-particles, and we can exploit them to gain some understanding. Consider an ensemble of particles all moving at the same speed. Each particle has kinetic energy, so the total energy of the ensemble is the sum of all the kinetic energies. Now imagine that one particle would stop moving. That particle contributes negative energy since it causes the total energy of the ensemble to decrease. We say that we have added a negative energy quasi-particle. We did not add a real particle since the total number of real particles did not change.
So each particle of Hawking radiation is accompanied by a negative energy particle falling into the black hole. Why is that?
The positive energy Hawking particle outside the black hole and the negative energy partner inside form a pair with zero total energy. That means no source of energy is required. In our day-to-day lives, we need to provide a source of energy, such as electricity, to turn on a light, but the Hawking radiation can come from nothing. Each Hawking particle can have any energy as long as the partner has the negative of that energy. Hawking calculated that Hawking particles would be emitted with various energies, forming a broad spectrum, like the light emitted by the sun. The mass of the black hole is concentrated into a tiny point at its center, so there's only empty space at the black hole's outer radius, called the event horizon. The Hawking radiation spontaneously appears in this void.
But why does the Hawking radiation spontaneously appear? You explained that each pair of particles has zero total energy, so it can appear in empty space. But why does it actually appear?
The answer is quantum physics. In classical physics, vacuum, emptiness, nothingness has no effect on anything. But in quantum physics, emptiness can actively cause things to happen. It can cause pairs of particles to appear. So it's the vacuum that makes the Hawking radiation spontaneously appear.
Quantum physics never ceases to amaze me. When it was made, was Hawking's prediction of Hawking radiation well accepted, or was it considered problematic?
Hawking's calculation was difficult or even problematic for 4 reasons. Firstly, it involved general relativity. General relativity is the most complicated thing that Einstein succeeded in understanding, so it's not so simple. Hawking's calculation is complicated enough that it is typically not taught in graduate physics courses, despite its importance. Secondly, Hawking combined general relativity with quantum physics, a combination which is not fully understood even today. Thirdly, Hawking's calculation relied on lengths which are essentially zero.
What are zero length, and what do they have to do with Hawking radiation?
To answer your question, let's consider the concept of escape velocity. Here on Earth, if you would want to throw an object into the air and have it reach deep space, you would need to throw it at 11 kilometers per second. As the object moved away from the Earth, it would continually slow down due to the pull of Earth's gravity and would finally stop when it reached deep space. Someone throwing an object from the event horizon of a black hole, the black hole's outer radius, would need to throw the object at the speed of light in order for it to reach deep space. In fact, that is the definition of the event horizon. That means that Hawking radiation particles reaching Earth must have been traveling at the speed of light when they were emitted.
So the Hawking particles were traveling really fast when they were emitted by the black hole. But what is the connection with zero length?
Now we must understand what quantum mechanics says about an object with mass traveling at the speed of light. According to quantum mechanics, particles are also waves. The faster the particle is moving, the shorter its wavelength. A particle with mass which moves at the speed of light has zero wavelength. The Hawking radiation, whether it is massive particles like electrons or massless particles like photons, has zero wavelength at the moment that it is emitted from the event horizon.
Why is zero wavelength problematic?
Because particles with zero wavelength are beyond our understanding. The laws of physics are thought to apply to length scales as short as the Planck length, which is a billionth of a billionth of a billionth of the size of an atom. Thus, we do not know the laws of physics for the Hawking radiation at the moment that it is emitted with zero wavelength. We do not know whether Hawking's calculation applies to such particles at all. It seems to be a hole in Hawking's reasoning. His calculation predicts that particles will be emitted with zero wavelength, but no one knows whether his calculation applies to particles with zero wavelength.
You described 3 problems with Hawking's calculation, but you said there are 4.
The fourth difficulty with Hawking's calculation is the issue of back reaction. According to general relativity, every object has gravity and pulls on every other object. Even photons have gravity. Thus, the Hawking radiation emitted has gravity. The gravitational pull felt by an object is the combined gravity of all the other objects. Thus, the gravity of the Hawking radiation combines with the gravity of the black hole itself, since they both pull on an object. In that sense, the Hawking radiation combines with the black hole and thus modifies the black hole which emitted it. That is back reaction. Hawking assumed a perfect black hole when he calculated the Hawking radiation, but the Hawking radiation itself modifies the black hole in some way, making it different from the black hole used to calculate the Hawking radiation. Thus, the calculation is not self-consistent. No one knows precisely how to calculate the effect of back reaction on Hawking radiation.
In light of all the uncertainty regarding Hawking's calculation, why don't we just look for the Hawking radiation emanating from black holes in order to prove or disprove his theory?
The problem is the low temperature of the Hawking radiation. The low temperature implies that the radiation is extremely weak. We said that a black hole radiates like an object which is 100 billion times colder than the sun, so the radiation from stars like the sun completely overpowers the Hawking radiation. Also, the radiation from the Big Bang is 10 million times warmer than Hawking radiation from a typical black hole.
So, is that the end of the story? Will Hawking's calculation remain uncertain for eternity?
Fortunately not, thanks to Bill Unruh. We see that Hawking's calculation was amazing since it combined general relativity with quantum physics. It gave a logical conclusion since it was consistent with Bekenstein's result, and it predicted that a black hole would radiate like any star, yet it seemed full of holes due to the zero length scales and back reaction. This caught the attention of the young Bill Unruh, who studied Hawking's calculation from every perspective and poked at it from every direction.
What did Bill Unruh say which helps us check Hawking's prediction?
While thinking of how to explain Hawking radiation to students, Bill had a profound insight. Hawking radiation is a general phenomenon which applies to a flowing fluid in addition to a black hole.
In what sense is a flowing fluid like a black hole?
Well, a black hole traps all particles, even photons. That means that particles within the black hole can't escape. Even if they are traveling outward at the speed of light, they will not be able to reach the event horizon, the black hole's outer radius. Now let's consider a fast-flowing fluid like a river. It is flowing very fast, faster than the speed of sound. That means that a sound wave can't move forward against the flow. It is like trying to swim against a current which is flowing faster than you can swim. You feel like you're going forward, but you're actually going backward due to the fast flow. That is what happens to the sound waves. They're trying to travel upstream, but they are actually going downstream. Like a particle in a black hole which can't reach the event horizon, the sound waves are unable to reach some point upstream. That is why a flowing fluid is like a black hole. It is a sonic black hole. It traps sound waves.
So a fluid flowing faster than the speed of sound is like a black hole?
Actually, a sonic black hole needs an inside and an outside, like a real black hole. That means that it needs to be like a river with a waterfall. Upstream from the falls, that is, before reaching the falls, the water flows slower than the speed of sound. But after going over the falls, the water flows faster than the speed of sound. In the fast part of the river, downstream from the falls, the water is flowing so fast that the sound waves can't travel upstream to reach the waterfall. They are trapped in the sonic black hole. Thus, the part of the river after the falls is inside the sonic black hole. In the slow part of the river before the falls, the sound waves can go faster than the flow, so they can move upstream, away from the falls. That is like being outside a black hole. It is possible to escape and to reach deep space. So we see that a flowing fluid with a waterfall is like a black hole. Before the falls, sound waves can still escape upstream, but after going over the falls, there is no way back.
You mentioned that for a real black hole, the particles inside have negative energy. Is there something like that for the sonic black hole?
Yes, there is. In the part of the river after the falls, the sound waves which are trying to reach the falls but are unable are actually very special because they have negative energy. Let's try to understand that. Due to its motion, the river has kinetic energy. The sound waves are moving in the direction opposite to the flow of the river, so the sound waves decrease the speed of some of the water, and that reduces the total kinetic energy. That means that these sound waves have negative energy. So there are negative energy sound waves inside the black hole and positive energy sound waves outside, just like in a real black hole.
Why are the sound waves with negative energy important?
Because there can be a pair of sound waves with zero total energy, which is the Hawking radiation for the sonic black hole. The Hawking sound wave travels away from the waterfall outside the sonic black hole, whereas the partner sound wave is trapped inside the sonic black hole and can't reach the waterfall. The total energy of the pair is zero, so no source of energy is required to create the Hawking radiation. This can happen spontaneously, just as Hawking predicted for a real black hole.
In the sonic black hole, why do the pairs with zero energy appear spontaneously? Is it quantum physics again?
Yes, it is. Hawking's quantum physics calculation also applies to the sonic black hole. So even though Hawking's calculation is problematic in several respects, we can at least check that it works for a sonic black hole in a laboratory experiment.
Bill Unruh's idea of a sonic black hole sounds like a great idea, but how does one create one in the lab?
The idea is to create a flowing fluid with a waterfall. We should then look for the spontaneous appearance of pairs of sound waves, where one member of the pair travels upstream in the part of the fluid before the waterfall, whereas the other member of the pair travels downstream in the section after the waterfall. There is only one problem. Remember that Hawking and Bekenstein predicted that a black hole should have an extremely low temperature. The same goes for the sonic black hole. The low temperature means that there should not be much radiation at all. For example, a warm object like the sun radiates a lot more energy than a cooler object like a person. Thus, we expect very few sound waves to spontaneously appear in the sonic black hole.
If there are so few sound waves, how can we detect them?
The sonic black hole should be devoid of sound waves other than the Hawking radiation, so that we will be able to discern the spontaneous appearance of the few Hawking radiation sound waves. That means that the sonic black hole must be extremely cold, since a warm temperature would imply many sound waves. In other words, a warm room has random sound in it, whereas a cold room has less. The same goes for the sonic black hole.
How cold does the sonic black hole need to be so that we can detect the very few Hawking radiation sound waves? Couldn't we just use cold water?
Unfortunately, that is not cold enough.
Could we use some liquid at the temperature of a freezer?
Freezer temperature is actually not so cold compared with absolute zero temperature, which is the coldest possible temperature. A freezer is only 10% of the way down to absolute zero temperature. We need to go much, much colder.
Okay, so how cold is the sonic black hole in your lab?
Our sonic black hole at the Technion is exceedingly close to absolute zero. In fact, it is less than 1/1000th of 1 degree above absolute zero.
Did you see the Hawking radiation?
Yes, we did. We observed the sonic black hole for 9 continuous days, which was the time required to discern the Hawking radiation. It was in precise agreement with Hawking's prediction, including the spontaneous production of the Hawking radiation due to quantum physics. We showed that Hawking's calculation was correct after all.
Amazing. Did you get to meet the late Stephen Hawking and share your results with him?
Yes, I was invited to a conference in honor of Stephen Hawking's 75th birthday party. He attended my talk, so I shared my results with him in that way. I spoke with him briefly at a dinner at his house, but it was difficult for him to communicate at that point.
What is the next step in your research?
Hawking's calculation included some approximations. In particular, he neglected the fact that gravity itself should be described by quantum physics. I would like to go beyond that approximation and include the effect of quantum gravity, or at least the sonic version of it.
It sounds to me that we need to schedule a follow-up podcast.
Just give me a few years.
Thank you, Jeff, for this fascinating conversation.
Thank you, Efrat.
You and our listeners are welcome to follow the Technion Physics Department's podcast, the Technion FIZZICAST, and to visit our homepage, phys.technion.ac.il. Thank you for joining us. Signing off, Efrat Sabach.